So at time t seconds, a particle p moves in the xy plane according to that vector function of t. That's better. Right. So we could write that a bit better as the velocity equals this function of t in the horizontal direction east, or the I direction. I don't know whether you've been encouraged to stick with the I's and J's.
I don't really know, honestly.
I hope not.
For this type of question, I don't know, but
anyway, yeah. At time t seconds, so at every time t, its velocity is given by t to the power of minus a half horizontally east and minus 4t vertically north.
Yeah. So.
And then they're asking us to find a distance. So we tend to think, okay, they've given us some velocity and we're expected to find displacement. So what's the essential relationship between velocity and distance?
Velocity equals distance over time. Is it?
Yes, for a distance time graph which has a constant gradient, the velocity just is a constant value, which is the gradient all along the line.
Oh, yeah.
But for a distance time graph with where the distance covered is varying continuously like that, where the velocity is also changing continuously, isn't it? At any moment, you've got a momentary velocity. Your speedometer in the vehicle is registering a particular value, and a moment later, you've slowed down or whatever. Yeah. Well, in this case, yes, you will have slowed down if I draw the point there, because your gradient now is
negative.
Lower. Negative even, yes. Oh, that's the point. You started going backwards if this is
backwards.
If it's a displacement time graph. Yes, good point. So in general, for velocities which are varying continuously, what's the relationship between velocity and distance? You can't say that velocity just is distance over time.
Total distance over total time or something.
Would give you the average velocity, yes. But this here is not giving you average velocity. It's not averaging it out. It's saying at any particular moment, the value on your speedometer is going to be...
Oh, sorry, is it the S equals ut plus half at? Is it? It's one of the SUVADs, but I can't say.
Yeah.
Actually, no, because that one's got acceleration.
That is true. And why is that true? Why is S going to be ut? Oh, no, not in this case. If you had constant acceleration, but here you don't. So when if you have constant acceleration, then y is S equal to ut plus half at squared. Did we touch on this last time? It's because the velocity, or the derivative of displacement, ds dt, was equal to a particular starting value plus the acceleration, the constant acceleration, times the time elapsed.
Yeah.
And then we found, okay, well, what's u the derivative of with respect to t? If u is a constant.
Oh.
In other words, for example,
it's nothing, isn't it? It's just
the derivative would be nothing, but what's it the derivative of?
Oh, ut.
Ut is what differentiates to give u with respect to t. You see, ut plus half at squared comes from integrating.
Oh yeah, no, we did touch on this. I remember. Yeah,
velocity.
Yeah. It's been a while, but yeah,
yeah, quite. So, and that works if you've got constant acceleration, but it also works if you haven't. It works for anything basically. any velocity function is going to integrate, because it is the derivative of displacement, it's going to integrate to give you the displacement function. So if the derivative here is t to the minus a half, then the displacement function will be what, do you think?
Oh, so you need to actually no.
What's going to differentiate with respect to t to give you t to the power of minus half?
T to the half. No, sorry, 2t to the half.
2t to the half is correct, yes.
Yeah.
Whereas if I sort of say, let's do minus 4t in the same way.
Minus 40 would have come from minus 2t squared.
Minus 2t squared. Okay. So so this gives us a displacement function, all right, of 2t to the half. But let's not forget plus c when we integrate, yeah?
Oh, yeah, yeah.
And what did I say? Minus, you said minus 2t squared, quite correctly, plus, we better call it d, hadn't we?
Oh, yeah, because they're different, yeah, okay.
Yeah. But the particle moves in the xy plane. Well, when t is equal to 1, so we could give an example of this and say, e.g., s equals, when t is 1, we'll have 2 plus c, won't we?
Yes, yeah.
And when t is 1, down here, what will we have?
Minus 2 plus d. D minus 2.
Yeah, lovely. I would do it that way too, yeah. And we're told that that is the point A. So where's A? Yes, A is the origin. When good. Right. So that is a distance of 0 from A.
Yes.
At time t equals 1, P is at a distance of 0 from A. So
yeah,
let's
okay,
have all
yes.
of our distances relative to A, shall we? Well, so A is the origin.
Yeah.
So if that's the origin, that means that C is, what do you reckon?
C is 2. Oh, no. Minus 2.
Minus 2, good. And D is?
2.
Yeah. So in actual fact, the full statement of the displacement function is S equals 2t to the half plus, or rather minus 2, sorry. And then this is 2 minus 2t squared.
Yep.
That's probably the best way to do this problem, I think, using column vectors. And now we can find the exact distance AB is just going to be its distance from the origin at t equals 4.
Yeah, so we just do the same thing with t. So we just put t as 4 now. Yeah.
And look, I went to the, look what I did. I made this. bear with me. So that's at t equals 1, it's at the origin.
Yeah.
Which means that at t equals 0, this is where it started.
Yeah.
You see, notice this vector here, we've got the horizontal component of its velocity is 2 root t minus 2, which is 2 to t to the power of a half minus 2, isn't it?
Yeah.
So it's always, in other words, from this general velocity vector, which I haven't bothered to construct, but it would have been, you know, you could do it like that. You could say the velocity is going to have 2 components.
Yeah.
And they're giving those components in terms of t. Well, you can do the same for the displacement. And when t is 0, when t is 1, both of the components are going to come to 0, aren't they? 2 minus 2 ones is 0. 2 ones minus 2 is 0. That's why at t equals 1, you are right at the origin there, at A. I should label that A, shouldn't I, the origin. I really should do that. Right. But then as t increases towards 4, you can see that this is what's going to happen. You don't have to see this while you're working out the problem. You probably wouldn't. I'm just saying it does help to realize that this displacement function that we made has a horizontal arrow and a vertical arrow.
Yeah.
And then when we're at t equals 4, we're at B, aren't we? When t equals 4, we're at B, and we're down here. And we can find that out by just plugging 4 in there, which we'll do.
Yeah.
What do we get?
Okay, so 2 for the top. I think that.
Yeah, I agree. That's 2.
And then 2 minus 16. I don't know. 2 squared at 4. No, sorry. 4 squared 16, 32, 2 minus 32, minus 30.
Oh, good. What have I done wrong then? Oh, it's 4. Oh, good. I knew I'd done. I was hoping I'd done something wrong because it wasn't tallying with what I thought. Right. Okay. 2 and minus 30.
Yeah.
Ah, right. So I wasn't right down here. We're here, aren't we? That's B.
Yeah.
But it does work. Right. So the distance AB?
So this is compared to, well, horizontally it's 2, and then vertically it's minus 30.
Yeah.
And that would be, so it'll be root 2 minus 30 or something.
Or something. The root is y? Why have we got a root here?
Because
Pythagoras, yeah.
Pythagoras. And then so it would be root 2 plus minus 30.
Just 2 and 30. How does Pythagoras work again?
A squared plus b squared equals.
Oh, that's fine.
Oh, yeah, no, okay, yeah, sorry, 2 squared, 2 squared minus 30 in brackets squared. 2 squared plus minus 30 in brackets squared, and then all of that rooted.
Oh dear. Sorry. Sorry about that. Yeah, plus the square of minus 30. or the square of plus 30, same thing. So the answer is?
The answer is 30 squared. 900 plus 4, 900, root 904.
Absolutely.
And I have, yeah, I have no idea if that simplifies or not very easily. But
me neither. It's mechanics, so you wouldn't be, you know, you by all means use a calculator.
Mm-hmm. I'm going to.
Much better to do it in columns. I mean, I did here. You can probably hardly see it because I need to change the color, but I tried using I's and J's there, but it's not as good as columns. Columns is much simpler.
Yeah.
Do columns. Yep. Right. So
I prefer columns as well. I think I's and J's just gets a bit weird.
Yes. Yeah. Bad news. Yes. So that is vector motion. Integrating velocity to get displacement. Yeah.
Yeah.
And
no,
then
maybe.
Sorry.
You know the textbook that we've used a couple of times.
Sure.
Other types of practice questions. Maybe we could have a look at some of those, like from that. Obviously,
Absolutely.
from the text. I have no idea what page it is, but.